There were 6 bells. There's still somebody. Well, I think everybody's in the room now. At least everybody that's trying to get in. There's 21. We're 3 people short. Whoops, here comes another one. Okay, we're still 2 people short. It's always so much fun at the end of the night to go through the list and see who didn't show up. Because I can never tell the name. There's too many names here. The other class I have, that one of the classes has only 8 people in it, and so it's easy to tell who's not here. Okay, give me a green light, just kind of as a hello. Okay, it looks like almost everybody found the green light. We still got one person kind of hanging coming in. Although I think he was in already. Must have dropped out. Okay. Not quite sure what the attendance thing is doing at the moment. It's doing strange things to your all's names. Oh well, let's get started here. December. Let's talk about the remaining classes because there are few. So we have tonight, which is 12/7. And tonight we're going to look at that homework you did, and we're going to work out some other example programs and things to start developing your skills so you can start to think like an assembly programmer. That's our goal. 12/9, which is Wednesday, we're going to review the ECHO program. We're going to learn some more stuff about processing and how it could be useful in using the ECHO program or something like it to give us a better user interface rather than just having that console that we have. And it's very adept at working with assembly programs. And then as a result of that, we will generate a homework assignment, which would be due on 12/14. And you can kind of think about it as it's a programming project. Whoops, not an OEF. Plus plus. It's going to be, it'll take a little more skill to do than the one you just did over the last gap. And it will count a little bit more. It'll go into the mix in a way that should help you because a lot of you need a lot of participation points and things. And that's where homework winds up. So you'll want to make sure when I give that out that you do it. So that'll be Wednesday night. We'll talk about that. We'll get you set to go, and then you've got 5 days to get that done. On 12/14, which is a Monday, we'll do a course review. So you'll want to have questions and answers. I'm not going to review everything if nobody has questions about them. I'll pick some things I know you need to know about, but some of the things that I just assuming you know you may still have questions about, make sure you come prepared to ask questions that night. Again, another chance for good participation points. Then on 12/16, we'll have test 3, which is, it's kinda like that, kind of the final. I'm not going to treat it like a final. It's just a third test, and it happens to count, I believe it's 30 points. First 2 were 10, this one's 30. Let's look at the thing and make sure.
Yeah, it was 30 points.
Okay, let's just verify here that I wrote that on the syllabus. I think I did. Yeah, the final exam, which is really test 3 for our purposes, is going to be worth 30 points. So that'll have a programming component to it and a question and answer part. The programming parts, it and the homework are both, you either get them right or you miss them. It's not, you got most of the way there. Programming doesn't work that way. And so you'll need to make sure that you have a working tested version of both in order to get credit for those. But whereas the questions, obviously, I will count the ones you missed versus the ones you got right. But that's a good 30 points that if you've been paying attention and you did well in the first 2 exams, you should fly right through this. If you had some problems by the time you studied and we've gone through a review, you should be back up to speed on that. So next Wednesday, the 16th, will be the final exam. Give me a green light acknowledging that you heard that date. Okay, good. And it's open book, it's open computers, it's the obvious rules, you can't cheat, and that includes, using copies of old exams I've given, or, talking with somebody or texting or doing anything that involves another person during the exam. But I haven't, well, I shouldn't say haven't had. We've had a couple people in here that are still going to get a big surprise at the end of the semester, but other than those, you guys have been very honest, which I admire. I think that's really good because, cheating on exams and things, when you're trying to get something that this may be part of your career, boy, that would be dumb. Because then you're going to get into your job sometime and there's not going to be anybody to cheat from and you're not going to know this stuff and you'll just fall flat on your face. So it would be a foolish thing to do anyway. So we're on the kind of countdown to everything being done. Anybody have any questions about that? Okay, well, let's move ahead then, and let's talk about the homework assignment that we had. I think my Arduino is plugged in. If yours is not, plug it in. Just be careful that you don't short it out. Make sure that it's laying on something that's non-metallic, non-conductive. And so just for a quick review of what we had to do, basically was we needed to generate the numbers which are divisible by 4 and they're not divisible by 8 unless they are divisible by 16. So that's kind of the homework assignment. So we would expect to see numbers like 0, 4. There'd be no 8. There'd be a 12. There'd be a 16. There'd be a 20. There wouldn't be a 24. There would be a 28. There'd be a 32. That type of thing. So we're actually just eliminating the ones which, 8 goes into, but 16 does not go into. And the goal here is not so much that this is a hard algorithm. Part of it is it's a typical problem you get where the problem can be stated more easily. But we'll kind of work from the other point of view, which is we're going to take and make it do literally what this says and then kind of tweak it a little bit as we tweak the algorithm. So we may do a couple variations in this. So I have a homework 1 folder. What I'm going to do is I'm just going to create a new folder here for my purposes called, let's see what happened. I hit some key that I shouldn't have hit, I can tell. Oh, it's HWK _10, so it's for this class. And then I'm going to put a copy of this into that folder. And I'm going to work in the folder. Okay, this other guy here, which is the old homework, I'll just stick over on my desk for tomorrow night's class. So in here, if we were to look at the code we were given, model is where the interesting stuff happens. What we see after all the setup stuff is basically we're going to load 18 with a 0, print it out by calling a function we have called print hex byte, which is basically the USART send things just collected into a subroutine. Increment, register 18, and branch back to the loop. And we'll just do that, printing out all the numbers until such time as we get to the not equal condition. And then we will follow through and just hang around here forever. So we load that on our box. And we run it, which is as soon as we loaded it, it starts running. We bring up the console window. And what we see are all the numbers from 0 all the way down to FF on the other end, we're assuming. Yep. So that program works in terms of feeding us numbers we could then work with. So one of the things we'd want to think about as we're doing a problem like that is how can we leverage that? Now, again, I'm not looking for optimization right now. We'll look at that in a second. And we won't even look at that too far. Well, basically what we want to say is if we were told we needed to use this code specifically, then what we would need to do is we would need to make sure that we only print out the values which are divisible by 4. Forget about the 16 and the 8 thing. Let's just go for, first of all, making it be a reasonable thing to do with a 4. So what we could do is we have the number we want to print in register 16 right here. It's rumored that print hex byte is only going to be needed, under special circumstances. So what we'll do is right before the increment, which is where we are, we're going to add a label. And the label should actually come in front of the thing that would prime register 16 to be printed. And I'm going to use a label right now of go on 1. Because what I'm going to do is I'm going to put a second label after the call. I'll go on 2. Now in my loop, I'm going to check to see if the number is divisible by 4. And if it is, I'm going to call go on 1 or drop in to go on, whichever happens. If it's not divisible by 4, I'm just going to go on 2, which would skip over that code that's there. So thinking like an assembly language programmer on what we would have to do, we need to get the value that's in R18 into some register where we can work on it. Now, just for the heck of it, I'm going to use a different register this time. I'm going to move, or N3C if I were, I'm going to move it into register 19. Now I can make changes to 19 without affecting the value that's in 18, or I can do things with it if I choose to. Now, one of the things we would need to know about is how can we check to see if a number is divisible by 4? Anybody want to tell me what a not the instruction necessarily, but what we would have, not we would have to do, but what we might do to tell something's divisible by 4, since we don't have a division instruction?
you could make sure that the bottom 3 bits are 0.
Would it be 3 bits or 2 bits?
Oh, 2 bits, I'm sorry.
2 bits, yeah,
2 bits.
because we want 4. If it was 3, it'd be divisible by 8. Well, we can use that later. Okay, so we could do that. Now, to do that, one of the best things we could do would be to modify register 19 so only those bits remain. That makes sense? That if I got rid of everything to the left of those 3 bits and left those 3 bits alone, I could compare them and see if they're 1, 0, 0. And if they are, I know the number is divisible by 4. So what I need to do is I need to write an instruction which, when operated against register 19, will make all the bits in the first 13 positions on the left be zeros. And the ones on the right, let them simply pass through unmolested. What Boolean operation do we have that allows us to do that? To block or not block data?
And?
Okay, the AND instruction. So what I could say here is perhaps something like AND immediate, register 19, with, and we could use a binary number here. Got 8 bits there, I believe. We want all of these bits to turn to zeros, and these 3 bits we want to pass through. Does that make sense? Hit the green button there if I ask a question like that, or the red one if it doesn't. Okay, so what that says is, now that I've done the AND, I could do a compare. If I do a compare at this point, then I'm going to be able to see whether, oops, what did I do? I can do a compare immediate of the register so that I can see that it's equal or not equal to that. So that's something like R19, there will be, okay, so if it's equal, it must be divisible by, I'm sorry, equal to this, it must be divisible by 4. Is that true? Okay, we got some green lights there saying that that would be true. Now, the question comes, aren't 8 and 16 divisible by 2 or 4? And if they are, there won't be a 1 in that position. So maybe we've written ourselves a bug here. Let's do a branch now. So we're assuming that if it compares equal, we're going to print. So not equal, we would jump to go on to. So let's run this. Well, first of all, let's see if it compiles. The way I type, that we could have all sorts of things going on there. We'll load it in. Bring up the console. Okay, now we're getting 4s and 12s, 20, 28. So we're not getting all the numbers that are divisible by 4. So that's interesting. Maybe there's a different technique we could use to identify those with 4, still using the masking. What I would wonder is it true that if I only let through the bottom 2 bits, I could then just simply test the register, and if it's a 0, it's divisible by 4. Well, let's just see what that did. Okay, well, this looks a little better. 0, 4, 8, 12, 16, 20, 24. Yeah. Now, I want you to look at that code because thinking-wise, thought-wise, the others seem to make sense. But when you think about it, that bit for division by 4, while Alex identified that correctly a while ago for 4, is not going to be true for all numbers divisible by 4. It'll be only those that happen to be, you know, when you're counting so that 4-bit does turn on. In this case, what we're doing is we're protecting the last 2 bits, letting them pass. If they pass and they're 0, that means that there might be some 1s over here. We don't care because anything that has 2 zeros in the last position are divisible by 4. And sets the flags, so we also don't have to compare afterwards. That's going to take care of setting the flags, and we just branch in. If it's not equal to 0, meaning these were not zeros, they're divisible by 1, 2, or 3, then, well, not 1, 2, or 3, 2 or 3, then we will have the ability just immediately to do our branch. So this reduced by 1 instruction, and additionally it let us go through, but it still doesn't satisfy the requirements we had. So let's build this up a little bit as we go here. One of the things we said was if it were divisible by 8, so I'm going to do a move into R19 from R18, and it again here, 0B, 0, 0, 0, 0, 0, 1, 1, 1, this time with 3 1s, but I'll immediately do the branch without a compare. So this is going to say it's divisible by 8. When it's divisible by 8, do we want to print it? Well, we got that 16 case, but other than that, we don't want to print it. So I can do a go on 2 here as well, right? Oops. Now, what we would expect to see now is not the final solution, but you notice we're getting 4s, 12s, 20s. What's missing here are the numbers that are divisible by 16. Any number divisible by 16 is going to have 4 zeros in the right-hand half. But we can take that to our advantage because we could do exactly the same code we were just doing for 16. In this case, if it's equal to 0 here, we do want to print it. So let's think about what we just said we're going to do. In each case, we're just saving the value in 16 so that when we increment it down here, we don't have to push it and pop it off the stack. We could, and then we could get rid of all these moves, but we still have to do a push and a pop, which isn't that expensive after all. But, and we'll try that in a second. Let's assume that this says, if our number is equal to 16, print it. Or divisible by 16, print it. Out of those that are left, If it's divisible by 8, don't print it. And if it's not divisible by 4, don't print it. So we'll print anything divisible by 4, including those divisible by 16, but not those divisible by 8, which meets the requirements. Let's see whether or not that actually works. Okay, 4, 12, 14, C, 24. Okay. We look close. There seems to still be some minor league problems. Let's look and see if we can figure out anything that needs to be adjusted. Okay, so let's take a case where we have a 0. Okay, let me actually, before we do, let me make sure that it's clear. Let me reload it first. What's that doing? Is my console not opening? I'm going to have to reopen the project. For some reason, my console is not opening up. Let me verify that it's talking to the machine. This poor little Arduino board that I have may have had one too many programs put on it. There we go. Okay, this is better. Now, the reason it didn't show the 0 a minute ago is I forgot to save. But 0, 4, we skip the 8, we go to 12. We get the 16, which we wanted. We go to 20. We skip the 24. We go to 28. We go to 32, which is printed. So this is doing precisely what we needed it to do. Now let's look again at the code. Now, because we keep clearing 19 each time, we could use a push after this to push 18 on the stack and then copy it and copy and copy. But this is probably, in an assembly language point of view, an easier way to make it happen for us is to just use it each time specifically. However, that doesn't mean this is the best algorithm that's out there. Let's, for a second, go to your, you do this, and we can look at my copy as well. But in the instructions, no, not this one, this one. In your instructions, over on the right-hand side are the number of clocks it takes per instruction. Let's kind of look at this for a second and kind of get an idea of how long this code is going to run. So somebody look up a move for me and tell me how many cycles that's going to take.
1 cycle.
Okay. How about an and immediate?
Also 1.
Okay. How about a go on 1? Or the branch of equal. What am I saying here? I'm giving you the name of the label.
1 or 2, depending.
1 or 2. Okay. So out of every 16, how many times am I going to do the go on 1? How many times am I actually going to go there?
15.
Well, this is the one that's filtering out only those numbers divisible by 16. So I'm only going to do this 1 time out of 16. So the branch will only happen 1 time out of 16. And I'm going to write it this way. I'm going to do 2 cycles, 16 out of the 16. The other, well, let me write it as how many times it's going to execute, and then we'll figure it out. We'll go 1 time out of 16 using it as a 2, and we'll go 15 times using it as a 1. It's a good way to write that over here and still maintain my width. Okay, so we know what this guy's going to be because he's going to follow the same pattern again. It'll happen once. It'll happen once. Now we're going to actually, at this point, only get here with really 15 of the numbers because one of them got kicked out by this branch here. The other 15 made it to here. And the only one we're going to reject with this one are the numbers divisible by 8 that are left, and there's only one of those in that 15. So 1 out of 15 gets rejected here, taking 2 cycles, and that would leave us with 14 out of 16 at 1 cycle. One here, 1 here. Now the way we wrote it, all of the ones that are not 4s, which are going to be about, there's going to be about 12 of them, 11, 12, 13, somewhere in that ballpark. Out of the remaining 15, this was 1 out of 15, so this is 14 out of 15. This is 12 out of the ones that remain here are going to take 2 cycles. And the remaining 1 or 4, let's say let's either be 4, 8 is gone, and 12 would be. So there's 2 of them left. Would leave us out of the 15 we have. So just rough order, this is probably more like 13. Those would all happen, and they would be different per time around the loop. Then we would have this move in the print, but we have to do that for all our answer numbers. Any of the rest, this happens for every single one. This function is going to be long, and this move is going to be a single cycle. So we'll just kind of lump this together and say that we have to do this for about 1 out of 256. We're probably doing that for about 1/64 of the number or something like that, where we actually print a number. There's only about 64 numbers print. Now, what we would do after this is we would count this up, and we would multiply the number we get by 256, because we do the loop 256 times. We would take this into consideration, basically saying that not all 256 took 2 cycles. Some percentage of them took this. The same thing here, same thing there. And I was loose with the numbers. I'm not trying to be precise. But what we could see is the biggest effect of this is we're doing it 256 times, and this is a big number. So what would really be nice would be if we could take this program and reduce the overhead of that last statement. And there is kind of a way we can start to attempt that. What we could do is we could say, why are we looking at all the numbers that aren't divisible by 4 to start with? Why don't, instead of incrementing down here, why don't we do an add immediate of 4? Now somebody should immediately throw their hand up and tell me why.
it could loop forever?
Well, maybe.
You said add or and?
Add. Well, we need the equivalent of an increment, but instead of adding 1, we want to add 4. And I don't want to write 4 increments. That takes a long time to do each increment, right? 4 cycles to do that. That should work, right? I mean, if I go increment R18, increment R18, increment R18, and I run the program, I should see the right answer, and I do. But that costs me cycles when I want to do, instead of all that increment business, I want to do it in a single instruction. I want to say add immediate R18 a 4. But if I try to do that, somebody raise your hand, tell me what's going to happen. Why is that different?
There is no add immediate.
There is no add immediate. That's exactly right. So I can't do that, but I still want to do that. I just want to do that. So a way to make that happen would be, let's change this instead of an add immediate into a subtract immediate. And instead of subtracting 4, let's subtract a negative 4. Now think about that for a second. Will that work? Okay, some of you are voting yes. Some of you are giving me kind of an I don't know. A couple of you said, oh no, don't do that. Disaster will ensue. Well, let's see. Let's run it. Okay, that ran. Let me see the output. Let me actually clear it and hit my reset button. If you ever need to do that, just clear it, then reach over on your Arduino and push the reset button, and it'll run again. And look at that. Those are the right answers. Okay, but we also know it just ran 4 times as fast. So if it was taking a second, it's now taking a quarter second. So we improved things simply by changing the way we were approaching the numbers. We knew we didn't need any of those numbers that are there. How about this? Can I also get rid of, since I don't have any numbers in that range, can I get rid of this test right here? Can I just get rid of that? Who says yes? Okay. Some of you are agreeing with that might work. If you think about it, we eliminated the 16s here, we eliminated the 8s here, and our purpose here was to eliminate anything that was not a 4. Since we have nothing other than 4s, if we eliminated the 16s and eliminated the 8s, then the 4 is the only thing left. So by not including it, let's look at the results we get. Yep, that looks like a right answer to me. So we've improved things. We got rid of a little bit of things, so those lines can go away. Let's actually clean them out of there. And I'm not going to keep the timings because we can just generally remember what took a long time and what didn't. It turned out it was that stuff we just deleted actually contributed a lot to the time. Well, we weren't printing anything, and this is probably the heavyweight guy here. We would go down here and count what he does. A lot of these are, you know, 3 cycle instructions, but they're necessary, and everybody the assignment said you had to print the byte out, so they would have to happen. Now the real question becomes, now that we've reduced it down to this, can we make it even better? Can we improve the algorithm even more? Okay, Alex, what do you think we can do?
So for mine, I used bit tests to check.
Okay. Okay.
The BSD instruction.
Do they take less bits or less cycles?
It's 1 per.
Okay,
it's less instructions.
Okay. Well, we'll try one of those in just a second. But with what we have right now, what can we do to improve what we have? We're keeping the 16s. We're eliminating the 8s.
Well, you could. I'm not sure if that'd work. Never mind.
Okay.
Would it be possible to eliminate the 16-bit altogether, since that would just be printed out anyway? The only numbers you don't need to print out are the ones divisible by 8.
Okay. We're trying to get rid of the ones that are divisible by 8. And in this guy finds the ones that are divisible by 8, right? So do we need the test for 16 anymore if we eliminate the 8s? Well, the answer is we really need to keep the 16, right? Because the 8s are going to take care of themselves if they we're done. So let's propose some code here and then think about it. When I do my first AND here, I'm going to still do it against the 4 1s. But rather than branching if equal, what I'm going to do is I'm going to do a compare. I'm going to compare 19 with a 0b, where the only bit I'm going to want to have remaining is a 1 followed with 3 zeros, which only happens for numbers divisible by 16, not numbers divisible by 8. So temporarily, if we make him, in the case here, a branch, and the branch is going to be equal to going to where we do the go on to stuff, and we look at this for a second. Let's semicolon these guys momentarily. We said grab the bits which say 1, 2, 4, 8, and look for the bit that's in the 8th position. If at the point you find something that has an 8 on the end of it, we don't want that. Go to 2. Everything else that gets beyond that should just fall into the let's print you. So let's see if that works. Let me clear my window, make sure nothing's there. And indeed, everything works as advertised. So the real trick to the question was, when this was originally phrased, divisible by 4, not divisible by 8, unless they're divisible by 16, what we're really looking for here is all the numbers, you know, as long as we're only looking at the ones that are 4s, in that set, any of them that aren't divisible by 8. And so by simplifying the actual expression of what we were asked for, and a business person would ask for it the way we wrote the question, we up to the programmer to realize that we can probably get by without those 3 lines. And we just test to see if the number literally has an 8 on the end of it. If it does, we don't want it. If it does, we can keep it. And we can actually simplify this because this label isn't being used anymore. And so we can actually pull the number off the end of that if we wanted to make it simpler looking. Make sure that compiles and runs. I shall clear it. Hit the reset. Oh, there it is. I couldn't find the reset button. And we look pretty good. Looks like things are working as we would hope they would. So this would be a really good answer. Now I'm interested, Alex, in your answer. Tell me what we would code in our loop here in order to make that happen.
Yeah, so I said bit test is bit store.
Okay, whoops.
The BST instruction.
Uh-huh.
And in the loop, I use BST R18 3, which tests for the 4th bits, the 16 bits, see if it's active.
Okay.
And then if it is active, or no, sorry, if it's cleared, it just prints the hex byte.
Okay, so you're basically looking at this bit.
Yes.
Yeah, excellent. Okay, your way works probably takes one less instruction, right?
Yeah, probably.
Yeah. Okay, don't publish that, turn that in, because otherwise it'll be being turned in and everybody else's homework. But hold on to that idea. That's a good one.
Okay. Okay,
so we use the AND. The AND's intention is to mask off the bits we're interested in, which we did, quite well. And we were able to get the timing down, because you can imagine this is going to run a lot faster than the original let's see all the numbers and throw away most of them. Right now, the only one that gets thrown away is the 8, but everything else is being printed and was needed. So this turns out to be a reasonably good solution. Now, if any of those that run are fine. So if your version did it a different way or did one of the earlier ways before we moved it toward I won't say a better solution, this is a solution. And if we're counting instructions, Alex has a better one than this, so we know there's even one in the world that's better in terms of count of instructions and instruction timing. But this turns out to pretty much state the problem in the way an assembly language programmer would think about it. Anybody have any questions about this assignment? I'm not going to collect it because it's more valuable to you than it is to me. If you didn't get it done, make sure you just kind of assign yourself as homework, redo it without looking at what we did, but thinking about it and see if you can come up with a working solution. Zach, you had a question?
Oh, the version I did involved like a whole division subroutine.
Okay.
Using subtraction. Use subtraction to
right. We could do that.
Yeah, it takes a
the
lot
problem,
more.
if we were to say let's print every 3rd number or every 7th number, then we have a different problem. We have to use division in some way to get those, in which case then it's probably going to be great to have the division subroutine in order to do that. That's not a bad solution. What we're taking advantage of here, and again, this is where thinking like an assembly language programmer kicks in, is we notice that the numbers are all powers of 2, and powers of 2 are always easy to work with when you're doing assembly language. There's nothing bad about having written a division subroutine. As a matter of fact, on this machine, for many of the types of things we do, we would use a variant of that. There's actually some algorithms which are a little bit faster, but the division subroutine for small divisions is not a bad solution. So if you did that, try doing it this way also.
All right.
Okay, anybody else have any questions or comments?
Well, if everyone else is sharing their solutions, do you mind if I share mine as well?
Go ahead.
I also did division, but instead of doing a subroutine, I used a logical shift right instruction because that will divide it by powers of 2.
Right.
Yeah,
and that's fine.
Doing it once divides it by 2, doing a second time divides it by 4, and then doing it a third time divides it by 8, and so on.
Right.
And I checked the carry bit to see if it divided evenly.
Okay. That's a perfectly legitimate way to do it as well.
Yeah, it just takes a bit more instructions.
Well, I
And
wouldn't
it would
worry
have to
too much about that. Remember, the algorithm is what's important. Once you get an algorithm that you want to write, you need to turn that into code. That's much more important than coming up with exactly what I would write. Remember, I've been doing this for 1,000 years. I think that I figured out that's how old I am. And so for me, I think differently. You know, when I'm writing in high-level languages, I think differently. So my high-level languages even look different than yours. You know, part of the class I do in the spring is to try to get you to write code in a high level that looks a lot like mine, because then I know you're going to get a lot of, you know, skill and be able to move forward with it, because I've been very, very successful with my style of programming. But for the assembly, right now, you're learning, you know, and so whatever you did, if it produced the right answers, that was an okay solution. Actually, Alex came up with one which is a little more than I expected people to come up with, which is a good thing. Okay, anybody else have any questions or comments? I appreciated those of you that participated. I appreciated your participation in this tonight. Let us move ahead. Okay, let me see. Which one of these do I want to do first? Let's go into our labs folder. Was lab 5 the last one we did? Somebody tell me yes or no.
Yes.
Okay. Let's copy 0 and make a lab 6. Let's see, where's my copy? And of course, we have to rename the INO file. Oh, I named it 56 there for a second. That's a lot of labs. And we'll open our models. Now we're going to clean some things up here to get ready to write some code. So first of all, I'm going to get rid of both the data and the BSS. I don't need either of those sections. What did I just do? Oh, I forgot to hit delete. Oh, that's right. This key doesn't work. And we don't need the, well, leave the vector for now. Just leave this. We're not going to use it this way, but leave it. We can get rid of the 2 globals down here at the bottom that initialize the BSS and the data. We'll come back and visit this in a minute. Okay, so now here's the goal of this particular program. What I want to do is same as the Blink program, but I want to do it in assembly, not in Arduino code. Now, to do that, basically what we have to do is we have to alternately turn this light on and off. So we're initializing it off. And so in my forever loop, I'm just going to place that line. And then I'm going to place it a second time, but change it change the first one to being a set. I'm not going to use this guy right here, so I'm going to leave this clearing the interrupts. But I'm going to leave it in for now just because, well, I thought I had deleted these lines. Okay. Okay, now I'm working in Notepad. That's probably my problem here. I should actually be working in the Lab 6 INO file. Okay, so can't go any lower than that. So let's just make sure that compiles. And it didn't, I don't think. So what did I do wrong here? Probably had to do with all the things I was deleting. Oh, yeah. Okay, in the vector, get rid of the lines that say LDS and STS. Get rid of those two lines. They were referring to something that was in the BSS that we don't have anymore. But that's why we pre-compile stuff, just to see the errors. Okay, so mine compiles now. If I load it onto the board, is it going to blink the light on and off? That's the question. Yes or no?
Won't it blink too fast to see?
Well, let's see. Okay, are you seeing that?
Mine's just off.
You think it's off. It's actually on and off. It's on half the time, off half the time. The only problem with that is the LED is not fast enough to keep up with our speed. Remember, we're running each instruction here at 1 over 16 million of a second. And because we're jumping back while it's clear, we're spending more time with it clear than we are with it set. Reverse the two and see if it gives you any light. Put the clear first and the set second. Now mine is glowing very dimly, but it's still not good enough to actually look at. So I'm going to put it back the way it was, set first, clear second. It's not a D, clear. Now what we need to do really is we need to write some sort of a delay. So what I'm going to do is rcall delay. And then after the other one, before we go back again, I'm going to rcall delay. And that means that the jump back will be so short it won't matter. Now if we try to compile this right now, we get an error. Had this name been defined in Arduino, we would have actually had it work, and we don't want that to happen. So if we write a function name, sometimes it's a good idea to make sure Arduino doesn't do it. But we can write ourselves a little delay function down below this. So let's write delay. Yeah.
You have it say R.
I think you meant to write the call.
I said R. I think I do too. Thank you. You know, this year, the holidays, I'm buying myself a new keyboard, or at least a bunch of keycaps. So I know what the keys do. So in our delay, what we basically want to do is we want to kill time. To do that, what we could do is we could make some sort of a loop and just burn up a bunch of cycles. So let's do a load immediate into register 16 of 0. And then let's create a loop. Let's put a no op. And then let's decrement register 16. And branch is equal to 0. But branch not equal, back to loop. And then if we ever get out of that loop, we're going to do a return. So let me try to scroll that up on the screen here. So put us 0 and 16. Then we're going to loop. In the loop, we're going to basically do nothing, decrement 16, and branch back. So we'll kill 256 of these plus 256 of these. That's 512, 16 millionths. Plus this guy from 15, well, for 254 of the 255 of the times, we'll branch back, which will take the branch time, which was 2 cycles, and one time it'll fall through. So this will add a few cycles. Now delay is still red. Let's try to compile it. Did it do it? Okay. Sometimes the reason this is because Arduino does have a delay function, and we are violating on its territory. So what I'm going to do is, instead of calling it delay, I'm going to call it delay 1. Just to won't accidentally someday pick up the Arduino version if I run the wrong linker script. And I'll recompile, make sure that didn't break anything. I don't think it did. Now let's rerun our program again and see if that delay was enough to make the LED look like it's on. What do you think? On or off? Green for on, red for off. Yeah, but it's not very bright, is it? And that's because we are, while turning it on, we're still, well, mine's actually pretty bright. But we're giving it a 50% roughly duty cycle, a little different because we're delaying and then doing the jump as part of the on time, or I guess that's the off time. So the off time is very slightly one cycle different. We, of course, could call delay multiple times. In both cases. Reload it. But you notice you still can't see it turning on and off. Remember, our purpose here is to blink, not to be on. We already knew how to turn it on. So what would happen if I took and put a bunch of these? And then down here I took these and I put a bunch of these. And then I run it. Well, it's still on all the time. So that apparently is not going to be good enough to do it. Well, I guess I could add in the loop, I could add a bunch more no-ops, put a whole bunch of them in there, and run. Oh, I have an error here. Well, I did what I was afraid I would do. I added so much code that I filled up all the programming addresses. So let me go back to one delay. I basically ran out of programming memory. When I do this, we'll recheck by compiling again. And we don't need all those no-ups. Okay. Well, this doesn't seem to be anything wrong with the code, but I sure can't see it blinking. It's blinking too fast. And we could grab a calculator, and we could say, well, we know we have 16 million instructions per second. So if I take 1 second and I divide it by 16 million, I'm going to get, there's micro, I'm getting 63 nanoseconds per instruction. So if I were to take this and basically do this loop, which is, you know, we're taking it every 256 times basically, and I multiply this times 256, it's still way down, each thing is way down in the 16 microsecond range, which is still way too fast to see. I'd need another 1,000 times that in order for it to be slow enough that I could start to see it blink. Because remember, we know that even at 15 frames a second, things start to blur together and you don't see you start to see artifacts of it blinking around then. So we could get it less than 15 frames a second, or 15 things a second, making it last that long, we'd be able to actually see it. So probably doing a delay loop is not going to be the best bet we got for making our light visible to see. So instead of doing that, what we're going to do is we're going to use a timer. We're going to use one of the built-in hardware timers to actually take care of calling this function. What we'll do, we'll change this to be a timer interrupt. And then we'll basically sit up here in a do-nothing loop, and we'll wait for an interrupt. When we do an interrupt, we'll just toggle the light to be the other way, which will be on, then we'll toggle it off, then we'll toggle it on. We won't use this on and off. Instead, we'll use a toggle way of doing it. So let me get us set up for that. First of all, I'm going to delete all the code that's inside the forever loop for the moment. And I'm going to delete my delay function down there. We don't need it anymore. I might have already deleted it. Yeah, I did. No, here it is. I don't need the delay. Okay, so what we have is basically we have our section saying do its global, here's do it. We say that the LED is an output, and we turn it off. We're going to clear the interrupts, meaning we don't want to have any interrupts, but that's already set for us, and we're going to be turning them on. So I'm going to get rid of that line. We'll come back to that in a minute. And then we're just going to stay in the forever loop. Now, in order for this to work, we're going to need to have an interrupt that can be called when the timer overflows. The name of that, and there's actually 3 timers. There's timer 0, which is an 8-bit timer. There's timer 1, which is a 16-bit timer. There's timer 2, which is another 8-bit timer. We're going to use timer 1, the 16-bit timer. So the name of the interrupt is going to be timer 1 underscore OVF underscore VECT in lowercase. So it's a timer 1 overflow vector. We're going to copy the name of that, and we're going to replace that. And let's do a save and a compile to make sure we haven't broken anything yet. Okay, now, what we need to do is we need to initialize timer 1, and then we need to tell it to turn on interrupts. And then we have to enable global interrupts so that the timer's interrupt will actually be noticed by the system. When we go in, the interrupt occurs, this will be called every time the timer rolls over from FFFF to 0000, this function will be called. So it's the timer is going to count from 0 up to 65,535 and then overflow. Clearly much bigger than the 256 we were using, but this also is going to be a precise count. So we can tune this to be a precise amount of time. If we want it exactly 1 second, we can tune it to exactly 1 second, plus or minus, 1 or 2 t-states. But it'll be very close. So what we need to think about is what happens in the interrupt. Well, when the interrupt happens, meaning the timer overflows, system interrupts are disabled. So no other interrupt can occur. It's then up to us to save the system's status register. So we're going to get the status register and put it into register 2, push it on the stack, and then in here somewhere we're going to toggle the LED. I'm just going to write a comment in here that says we need to toggle the LED. Then we're going to retrieve register 2 and restore the system register back to whatever it contains. So all the flags get preserved across the interrupt. Then we're going to return from interrupts, because we said return with the I there. It will reinitialize or reestablish the interrupts globally so that any other interrupts that occur, if we were using, for instance, the USART or something, we could get those interrupts. But also it's ready so the next time the timer overflows, we can see the interrupt. Everybody reasonably clear about what's going to happen there with that interrupt? Okay, good. Now, one of the things we know we're going to have to do is right before we enter forever, we're going to need to set the global interrupt flag on. So instead of clearing interrupts, we're going to set interrupts so they happen. And then we're just simply going to sit here and spin around waiting for something to happen. And since we don't have any work to do, we'll just basically just keep jumping to forever. Meanwhile, anytime the timer, which is running independently of us, overflows, this routine will be called. Our routine will be interrupted. This will happen, toggling the LED, and then it exits. We'll continue woofling around this loop. Everybody understand that? That's important. That's a hardware issue that we have to be very clear that we understand. Okay. So we now have to think about how are we going to go about making timer 1 do what we need it to do. So very much like the code we did to set up the USART, we need to set up the USART to receive characters, because the sending characters didn't involve interrupts, only sending or receiving did. We need to go to the data sheet. And I'll maximize it here, and we need to go to, I think it's chapter 16. And inside of chapter 16, if you did the bookmarks here, you want to open it up and go down to the last thing called register description. Not register description. Oh yeah, register description. That's the correct one. And this will talk about the setup registers that we need to be involved in order to make the timer work. Now the timer on an Arduino are very, very powerful. Basically, each timer maintains 2 individual functional entities if you're not using it just strictly as a timer. And the other functions this timer 2 can do are, number 1, it can count up to a number which is not a regular overflow and overflow early. So you can use it to tweak a timing by simply saying, I'm going to start at a particular number and count up to a number and overflow. To make it easy, you can do that one of two ways. One is you can say, I'm always going to overflow at 4Fs, and I'm going to preload the counter with a number that's not zeros, and just let it count a little short of the number it would have counted, so that I can tune a time that's less than what the normal timer overflow would be. The other way is I can set a top value and say I'm going to always initialize it to 0, and when it hits top, that amount of time will have gone by. So it depends on which way you want to do the work. Do you want to subtract it from 65K and have to figure out what that value is, or do you want to have to figure out what the time is counting upwards? Both work and both are useful. Another thing this can do is it can automatically produce a pulse width modulated signal, meaning it can produce a clock which is on and off, so the combined amount of time on and the kind amount of time off is equal to some value which you want to consider to be your pulse width modulated frequency. Then you can determine of that frequency, how much of it do you want to have on? What's the duty cycle? 10% on, 20% on, 50% on? That's very useful for using the brightness of an LED or the speed of a motor. It's much more efficient than controlling the current by simply letting it be on some amount of time as opposed to changing the amount of current. And it effectively does the same thing. If I'm only on for half the time, effectively you're getting 50% of the current. But I don't have to worry about putting in variable resistors or transistors that are controlling that. The counter can do that for me. We are not setting ourselves up for PWM because that particular LED on your board does not have the little squiggle next to it, meaning that one does not support PWM. Now, we also can say, I want to capture a value. And I can preload a value, and when a pin goes high, I can capture the value that the counter had counted to when the pin went high. That way, I can capture an external event and know how much time occurred before it happened. We're not going to use that feature. And there's a couple other features that the Timer 1 does. Timer 1 is 16 bits usually. We can make it count to less numbers, but usually you'll think of it as being the powerful counter on this machine. We also can often control the counter by an external pin, so instead of becoming a timer, it becomes a counter. We're going to use it kind of as a timer, but we're going to use it as a counter that overflows, and we're going to know what the time will be. And because of that, time and count kind of blur together, and we could use either term to describe it. So in the register, which is the timer and counter control register A for Timer 1, we've got 6 bits which can control something. We have the mode we're going to use if we're doing a compare mode operation for channel A. Remember I said it can have a channel A and a channel B for each timer. And we have those so we can set timer B to be doing, or mode B, for the second part of the compare mode. So we've got 2 things we can set up there. Since we're not using special features, we're not going to have to do anything special, but we got to make sure we don't set it to something that causes a special feature to occur. We also have a couple bits which are used in conjunction with some other bits elsewhere to determine when we're doing non-PWM type of things on our compare registers, some specialization of those. So let's just look at what the bits being set mean. In the A1 and A0, or the B1 and B0, if we set them both to zeros, we're doing normal port operation, meaning the ports that we're attached to, OC1A and OC1B, are not going to be affected by what we're doing. We want that to happen. We don't want our changing the timer overflow to affect any external devices. So we're going to basically make the port operate normally and not affect these 2 external pins. These pins would be used normally for PWM, but they might be used for other, like compare functions and things like that. We, however, could set them up to toggle that bit when we have a match on the compare, or we could clear the bit when we want to match the compare. Now, the compare register is kind of, think of this way. If we were going to let the counter count from 0 to 100, we could put the compare at 50, and then when we hit 50 counting up, we could cause it to toggle. So if it was off, it would come on. If it was on, it could go off. We also could set it so that at the spot, we don't know what it is right now, so we're going to specifically say we want to set it to a low level by clearing it, or we want to set it to a high level. Our choice of the day is going to be to set it to zeros because we want normal port operation. Now, if we were running in non-PWM, or if we were running in one of the PWM modes, like fast PWM, those pins take on different meanings. Of course, we've set it to 0, so we're going to get normal port operation no matter what, because we're using normal port operation. If we were going to be setting the output mode so that we were doing a specific PWM mode, again, we're doing port 0, we're doing bits zeros, so we're getting normal port operation. But there's further configuration we could do if we wanted to have phase correct PWM, with phase and frequency actually, rather than compare options. And then finally, if we're generating a waveform, those last bits, in conjunction with another bit over here, WGM12, will allow us to set whether or not we're doing pulse width modulation phase correct, counter timer type of operations, fast PWM, regular PWM of the fast and frequency correct variety, or a different variety in flavor, just regular PWM down here. We're going to be setting it up to do normal PWM, so we don't have to worry about any of this right now. However, when you scan through Chapter 16, which should be some of your homework, don't read it in detail, but scan through these charts. You'll see there are other interesting modes we might get into. Timer counter register B has some other bits in it. It has the top 2 bits that we were just referring to here that we're going to be setting to 0, 0. And it has, over here, the prescaler. They become very useful to us as a counter. Now, these 2 bits we're just going to set to 0 because they have to do with whether or not an input pin should be attached to a noise canceller. Since we're not doing input, clearly not. And since we're not doing input capture, we don't have to worry about whether it's on the 0 edge or the 1 edge. So we'll just leave it set to 0. However, we do care about the prescaler. And we're going to have some bits down here that we need to look at when they call them clock select here. Here's our clock select. If we set them to all zeros, basically we have stopped the timer, meaning the timer is not being used, so it'll never overflow. However, if we set them to 0, 0, 1, we're going to get no prescaling, which means the clock is going to advance by 1 16 million times a second. If we set them to 0, 1, 0, they're going to be divide 16 million by 8, so it'll be every 2 millionth of a second. We set them to 1, 1, we divide 16 million by 64, and that's how often it will advance. So let's look at the calculator and see what that would be, for example. Where's my calculator? There it is. So if we took 16 million, we divided it by 64, we would be we would be changing the timer 250,000 times a second. But our timer needs to overflow every 65,536. So if we divide this by 65,536, we'll see that we are going to be only overflowing approximately 4 times a second. But since we're going to toggle instead of turning it on and off every overflow, that means we need to divide this number by 2. Well, actually, yeah, we're still doing those. So divide by 2. And we're really going to take just about 2 seconds per state, meaning it would be 2 seconds low, 2 seconds high at that particular rate. Now, my guess is that when we do our math and we add the extra instructions, we come back and recalculate this, we're going to see basically visually that this is going to be a doable number. This will be faster, but will it be too fast? We'll have to try it to see. This will be considerably slower because it's 64 times slower than that. So we've got some playing around, but just remember that we're the clock prescaler needs to be set to 011. Just remember that. Register C doesn't need any particular thing setting because the 2 bits that are set need to be set to 0 and they don't really affect much. When we count, there's a 16-bit counter that's actually doing the counting for us. There's a low byte and a high byte. We need to preload this. Now, there's some rules about 16-bit I/O that you need to know. If I'm writing to a 16-bit hardware register, I need to do them in a specified order. And let me double check my notes to make sure I tell you the right order. Yeah, I remembered it correctly. We write high byte first, low byte second. High byte is actually shared with a bunch of devices on the machine. So if you were to only write the high byte without writing the low byte, it just gets saved. When you do write the low byte, then all of a sudden it actually takes and causes both to be written to the hardware. Now, if we're reading from a register, a 16-bit register, we do it in the other order. We read the low byte first. Then the high byte second. What it basically does, when you tell it I'm reading the low byte, it kicks in and forces the high byte to become ready so you can then read it. So you pretty much need to do that. We'll have to do this. We'll have to write 0 at least once to this register to get it at a value that we know what it is when it starts. Then later on, we don't have to read the register because we know when it overflows that it's at 0. But in this particular application, we'll have to write zeros to it in that order, high byte before low byte. And this is the register names we'll be using, high byte and low byte. And then finally, we have some registers which have to do with if we were using the compare function, which we're not, or if we're using the capture function, which we're not. Now, we do have this interrupt mask that we are concerned with. And in the interrupt mask, we need to make sure that the interrupt that we turn on is the one that has to do with timer counter overflow interrupt enable. And if we had an interrupt routine, we could later check to see in this register, is that the interrupt we're in? Because we wrote, let's say we wrote an interrupt that serviced both this and that. We could use this function and register here to determine which one of those two caused the interrupt. But we don't need to do that because we're going to only have the one interrupt. And I think that's the registers. I don't think there's any more listed in the book. So now I guess what we can do is we can go think about code that can do those sorts of things we just talked about. put this back out of sight somewhere. So as soon as I get into the code here, after I've done my initial clear, I'm going to actually, let me put an extra blank line in there. We need to do our business. First thing we want to do is we need to clear out TCA or TCCR1A. Okay, so to do that, a way we can do it is we can do a store into TCCR1A. A 0. Now I can't do that. Why can't I do this?
Because I believe you need a store from a register.
Right, we'd have to store from a register into the SRAM. Now, I'm lazy. I don't want to load register 16 with a 0. So what I'm going to do instead is I'm just going to say from R1. Because we said R1, after it's been initialized, if we ever change it, we're in trouble. We're going to make it just contain a 0 all the time. So I can just go there and get a 0. Now, I want to work on register B. So I can load immediate into let's put it in register 16. This is a nice handy place. I have 2 bits that I want to turn on. Who wants to tell me what I just did and why that does anything? I'm actually, because it's more idiomatic to not put a space here. What did I just do?
You shifted the ones a certain amount of numbers.
Okay, how many
to the
numbers?
left.
Mm-hmm.
I have to pull up the chart because I don't remember that.
That's okay. You're exactly on the case. If we go to our register B, which is where this stuff is going to be stored, let's scroll back to register B. Go there without going too fast. Get close. That's A. And A, we cleared everything out of it. B, these 2 bits are getting set to 1. Remember we said this is the prescaler? We wanted them to be a 1. Everything else was zeros. Well, if we go to the header file, CS11 is defined as the number 1. CS10 is defined as the number 0. So what this instruction said was, take a 1 and shift it left 1 position. Take a 1 and don't shift it left 0 positions. So basically I just did that. I created that as the immediate data. This happens at compile time, so this is what the instruction has encoded in it. It's going to get it picked up, put into register 16, and now we need to put it into the correct register. So now I can do a store into TCCR, whoops, 1B of register 16. I'm going to check my, see if I haven't broken anything yet. So now we've taken this control register and we've set it up on the thing to say, I want it to use 011, which is divisible by 64. So the speed the timer is seeing from the clock is 64 times slower than the system clock. And we did that so that we'll be able to see our LED blink. It has to be visible. Now we want to set up our interrupt mask. So I can do another load immediate. And I'm going to put it again into register 16. And what I want to put into here is a 1 shifted over POIE1, which is the timer overflow interrupt enable 1. So I'm going to take that 1 bit and turn it on in the correct register, and the register was the timer mask register. And what we're going to store it here is, the name of that register was TIM SK1, and put register 16 in there. And again, let me check that I didn't type something wrong. Okay, so now that we got the timer mask, we got the prescaler turned on, we said to register A we didn't want to do anything. We don't know what the counter has in it. So what we need to do is we need to take and we need to store zeros into the high and low buckets of the counter. I can't write the instruction I want to write, right? I'm really sitting here wanting to take and put store at, timer, what's the name of these registers? TCNT1H, register 16. I really want to say that after I have said, actually I don't know, I want to say register 1. And I can't do that. Anybody remember why?
I thought register 1 was reserved for something.
It is a 0. I want to say store a 0 at that timer or at that address. Why can't I do that? The reason is because we looked last time at this instruction, there's not room to store more than 4 bits. And the 4 bits start at register 16. So I can't store anything from register 0 to 15. I have to start at register 16 to 31. So this is going to minimally have to be register 16. But if it is, I'm going to have to clear that register to some value. So I could move 2 to 16. Or I could do, I could say XOR register 16 with register 16, because that does the same thing, right? If you XOR something with itself, it turns out to be all zeros. But they thought of that. They wrote an instruction called clear, which is exactly the same thing I just wrote, which is a XOR of 16 to 16. If you look at the encoding, it's exactly the same. It's up to the assembler to know to use it. So I can clear 16, and then I can store 16 into that. 16 is still a 0, so I can also store it at the timer counter low byte. I do low byte after high byte, and then I can set the interrupts. Now, if we got everything hooked up correctly, let's see if it compiles. See if that loads on the board successfully. It doesn't have any memory errors or anything. Now you'll notice one thing. What's the one thing?
The light turned off.
Yeah, the light turned off and didn't do anything. Let's go down to this interrupt routine where it says toggle the LED. Instead of that, let's rcall and let's call USART send. And before we do that, let's do a load immediate into register 16 of capital letter A. And before we do that, let's push register 16 so we don't wipe it out. And right before we pop it, let's restore register 16. So your interrupt now should look like this. We save the status register in register 2 and push 2 onto the stack. We then push 16 so we don't wipe it out. We load immediate an A into 16. We call USART send, who's preserving its registers. Pop 16 back, so we've got the original 16. Pop 2 back, so that we've got the value we need, and output it to the S register. Now, we have to, by agreement, have agreed that register 2 gets clobbered. The original register 2 you called me with doesn't exist anymore. Even though I popped it, I had already changed it in the first instruction. So register 2 is one of our rules, is it's going to get clobbered by any interrupts we have. But since we know that, we're not going to use register 2 for anything other than interrupts. And then we return. So now let's run. If I typed everything correctly, I'll load it on and see what happens. And if we bring up the console, we should see some A's clicking, which means the interrupt is actually operating. Give me a green light if you've got the A's on your console there. Okay, now we don't know. I'm going to close that window because I don't need it. We don't know if the timing is right. All we know is this function is getting called, because this function itself takes a long time to execute. Normally, except for debugging, you would never put something that was long and executed a long time in an interrupt. Part of being an interrupt is to get your business done and get out of there. You know, get out of Dodge as fast as you can. So let's clean this up. Get rid of the push, the load, the call, and the first pop. And that should leave us with the fact that we need to toggle the LED. Because that's the one thing that doesn't happen yet, right? We'll have to write an instruction here to do that. To do that, I've got to give you some more information about our inputs and outputs, stuff that we haven't talked about before. I'm turning the page here to make sure that I remember it correctly. I always look it up. I never trust remembering this chart. I think we can use this. This was your first fact to know and tell. Okay, on the pins that can operate as inputs and outputs, they have registers which are used, which are called things like port, data direction, and pin. Now, let's start with data direction. Data direction on a read returns the data direction, meaning is it an input or is it an output? If you write to the data direction register, if you write a 0, it makes the pin an input. If you write a 1, you'll make the pin an output. And they can be changed any time as long as you know what you're doing. Now, we've seen a DD register before. If you look up here, right? We wrote to DDRB. I guess there's actually an R in that name. So let's insert that. DDR. Well, I remember why I didn't do that. I had one of the kids in my class one year, the favorite game was Dance Dance Revolution, and every time we did that, he'd start dancing around the room. Okay, so read gives back, I should say that maybe. So if you set it to be a 1 and you read it, you're going to get back a 1. You set it to be a 0, you get back a 0. You just read it, it'll be the default for whatever that pin is. Now, on a port, and like port A, port B, port C, if we read, we get back the output buffer. Now the output buffer is basically the last thing I tried to write to the pin, whether it's an input or an output. So it reads the output buffer. It does not read what's on the pin. So if you use the port, you're not going to be able to see what's attached to the pin. You're just going to see whatever the last value was you wrote to the output buffer. Sometimes they match, sometimes they don't. That's part of the designing it. Now, if the port is set for input, and you do a write a 0, you're going to deactivate any pull-ups that are on the internal part of the pin. If you write a 1, you're going to activate the pull-ups. Now, if you think about for a second, what does that mean? If I were to take, let me grab a thing here and draw you a picture. A pin on the side of a chip, and we're going to hook it to a button. So I'm going to put a button here. The button's open or closed. When it's closed, we ground it. And we generally ground it through a resistor or something, so that the current flow is limited in terms of it being an output. Now, the inside pin is basically the same as open collector, meaning that when it's not attached to anything, it doesn't read low, it doesn't read high, it just kind of reads, don't know. So in order to fix that, normally we attach an external pull-up pin here. So unless you're grounded, this is pulled up to 5 volts, for example. So it would see things. But let's assume for a second you didn't want to attach an external resistor here. Well, inside this, picture that there's a transistor sitting here, and it can go to ground. What you can do is you can enable an internal resistor to replace this guy. So if you don't install him, you can instead say, turn that one on inside and make this be able to read 5 volts anytime nothing's pulling it down, which is what this is used for. If I need it to be there, I would activate the pull-up by writing a 1 while I'm configured as an input, meaning while I'm configured to read, but I'm going to do that on port, whatever, port B. Kind of complicated, but nevertheless something we need to know in order to make things work. Now, if a port is configured as an output, I could write 2 things. I could write a 0, which means I'm writing a low output on the pin, or I could write a 1, which means I'm writing out a high. The other choice we have is the pin itself, the pin B, whatever. If we read it, we actually read the value on the pin. Now, amazingly, if we write to it, we can write a 0, which says do nothing, or you can write a 1, which says toggle the pin. Bingo! We found what we need. We have to use the pin, and we could be either configured as input or output. We happen to be configured as output. Well, which is going to be, we wrote a 0. The port, whatever it is, doesn't matter, because if we write to the pin a 1, it'll cause it to toggle the pin. We're using port B. Therefore, we should be able to write to pin B. And what we should be able to write is, at that particular pin number, we should be able to write the value 1 to cause the toggle to occur. Now, we need to know specifically which bit we're going to do. So it's not as simple as just, oh, we'll just write to all of it and make all of its pins toggle. We're very picky about which pin we want, and we only want the one that is specific to us, and that's going to be on the pin 5. But because of the fact that we want to set the bits in our list of things here, the pin we actually need to go after is not going to be pin B, but it's going to be pin 5. So I should be able to do, just as I did with all my clears and things up there, a set bit immediate. Or not immediate, set bit IO. And just like I'm using up here, which one I want to actually set, I'm going to need to do the same thing down below. So pick the register, and the register we said was going to be called pin B, and then the pin we're going to set itself is going to be pin B5. And it just uses the name. It doesn't need to be masked or anything because it's one of those special instructions. But because it's a special instruction and the address here, pin B, is in the data space, we need to put this back into the IO space. To do that, we need this. Of course, close the parenthesis. So it said, give me the data address of pin B, turn it into an IO address so I can use an IO instruction against it. And what I want you to do is set that bit inside that pin. And this takes as a parameter the bit number. So you just simply can use it, as is. So let me see if everything compiles at this point. And let's put this on the board and see if we're in any better shape. Okay, I don't know about you, but I have a blinking LED. Give me a green light if you got one too. Now, we said that we're going to manipulate the timing here. So this was divide by 64. Let me actually make a note out here to the side. Divide by 64. We had the case, I'm going to increase that instruction by 1. We said that if we set it to this, how can I hit 1 key and get 3 characters? I don't get this. We would get a divide by 8. But this guy would, of course, have to be a 0 now. But you can't code a 0 here meaningfully. So really, that would go away. We don't need that. So this guy here, second one does the divide by 64. First one does the divide by 8. So let's comment out the second command there. Let's reload it and see if we get the divide by 8. Maybe too fast. If you got epilepsy or you respond to flashing lights, don't do this. And I'm serious about that. Don't do this. I can't see it blink, but some people can. Okay, so that would have been too fast a number for us to use. Let's comment it out also. And let's put a third line in, because the next one after that was divide by, what was it, 256? We'll have to look at the manual to see. That's down here just a ways. Yeah, 256 is 100. Notice this uses a third bit. But we want 100 for 256. Oops, not that. So to get the other one, I've got to put another one of these things in front of it. The first one of which now, this has to be 12 instead of 11. And this would be divided by 256. Which means I'm coming out the first two, leave that one in. And loading, if it didn't spell something wrong. It should run, but it should run considerably slower. How many times slower? Question is, will we live long enough to get it to be bright again? It should take 64 times the time we were doing when we were 64. Okay, assuming we got all of our bits set correctly. Mine hasn't turned on yet, so I don't know about yours. Has anybody gotten yours to get to the first blink yet?
I did.
You did? Okay. Yeah, mine's not doing it, so I don't know if, I think I've got my code right. Oh, let me see, did I do that? No, I did ORS, okay. Okay, well, let's put it back to 64. I'm not even going to leave that one because either there's a bug or I made a typo somewhere. I'm not even going to keep that guy. I'm just going to keep the 64 guy around. Now, what if we wanted, and let me just double check that that still works. Make sure I didn't delete something. Yeah. Now, what if I wanted to have it blink twice as fast? What could I do? Yeah, Joseph?
Would you divide it by half of
Well,
would you
divide what
it
by
by
half?
32?
Divide what? Well, see, I can't do that because there's no options for setting these values that give you a 32. The only choices we have are those guys. We can divide by 1, 8, 64, 256, or 1024. We have no other choices. But I
So
want
would
it
you
to
slow
go,
it down? Oh, sorry.
I want to slow it down, but did I say twice, half the speed or twice the speed? Half the speed, right?
You said half, yeah.
Yeah, half speed, so it's twice, it takes twice as long.
Oh, I'm not sure.
Okay, well, that's fine. One of the things we could do, oops, that guy's old news. Is the reason that if we wanted it to be, I'm gonna forget whether I'm saying half or twice, so because there's different solutions to both the problems. Let's do the one where we want it to blink faster. If we want it to blink faster, what we're saying is we want it to go to the interrupt sooner, which means that the values we're loading in here, we're starting from 0 and counting to 65,536. We need this number to be a bigger number, or else we're not going to enter this sooner. We'll still be the same amount of time. So let me take a first user type of approach to this. We need to take a number which is roughly half, let's say, of 65,536. We know what that is. It's 1 power 2 less. So I need to load that into the two parts of the register. So let me put part of it, and we'll use register 16 again. I'm going to have to load high part here, and I'm going to have to load the low part here. The trouble I have with this is the fact that I don't have the ability to put a 64-bit number into this or this, but I do have a way of splitting it in half. Do you remember that last time? We have a high 8 of what's half, about roughly 732, 768. And I also have the ability to put the low 8 bits in the other. So this will pick up the top bits, this will pick up the low bits, this should put it in the high, this should put it in the low. We check to make sure it compiles, in case I misspelled something. Load it up, you'll be disappointed. It looks like it's roughly going the same speed it was. Anybody have an idea why?
Because you have to, because that would only do it for the first iteration.
Exactly. Exactly.
Set it
So we
each time.
need to take this code and do it every time we have an interrupt. Let me fix that line first. So I'm going to grab all that. I'm going to go in the interrupt. After I toggle the LED, the very last thing I do, right before the pop has to be afterwards, I'm going to do those instructions. Now, I clobbered 16, and it would be nice if I could use 2, but load immediate doesn't let you. So what I'm going to do instead is right here, while I know 16 is still good, actually let's just do it up here where we save 2. We're going to push 16, because I'm going to use it. And right before I pop the 2, I'm going to restore it. Now this is close, but it's still not perfect. Anybody want to tell me why it's not perfect? Where's my save? Why is it not perfect? Well, this isn't tricky particularly, but if you think about it for a second, we're guaranteed, unless there's a higher priority interrupt going on, to get to this first line of this instruction every time we overflow from 65, 536, or 535 to 0. So that's a very precise timing getting to that spot right there. We're always updating at exactly the same spot, meaning that the new count we have gets initialized when we write this low register right here. There are, however, a few instructions that get executed before we go back to the thing, and they may or may not be decrementing from this value. We're still guaranteed we'll get back in the function again, but the number we took and picked here, we're going to have to base it on how often we get in here, not based on how many instructions are inside this, unless we get so fast that we can't execute them all in time. In our case, we got plenty of dead time between ticks, so that should work. Let's load that and see if we got any faster. We might have an error still. Now mine's going about twice as fast. Now, if we wanted it to be slower, we're in a little trouble. Either we got to make the prescaler, slower, and we can do the counting thing, but we can't reach the number we want from 256 division. So that won't work. So you have any other proposals for how we might go about making the thing be twice as long? Tatiana, do you have a suggestion? I saw a green light come up there.
No, not yet, Professor.
Okay. Well, if we wanted it to be twice as long, we want to actually execute this instruction right here, wherever it is. Where's the toggle? The right here. We want to execute this instruction right here every other time we enter the interrupt, right? Do you think there's any way that we could only do this every other time? Alex?
You can possibly store a value somewhere to compare against. So you can store, on the first iteration you'd store 0, or you'd store 0, and then on the second iteration you load it in and increment it, something like that.
Okay, I like that. I like that a lot. So we could use basically the same thing as a toggle. Just something that if it's a 0, don't do it. If it's on, no. So we could create another variable, or leave it in a register. Let's put it in a register for now, so we don't have any data space unless we have to put it in a variable. So somewhere when we're initializing things up here, we're going to pick a register we're not using, and let's put it in the registers above 16. So I don't know. We're not using register 20 for anything right now. Before we turn the interrupts on, let's cause register 20 to be a 0. How can I do that? I could do a load immediate, I could do a XOR, or I could do a clear. Everybody good with that? That will make register 20 contain a 0? Now, if we want to just simply add something to it everywhere, that would have to happen inside the interrupt, every time we got in the interrupt. So let's go right after we have dealt with pushing the registers. And let's increment register 20. Now, I don't have to worry about restoring 20 because I want it to keep the value in and out of the thing, so I don't want to save it and restore it. I'm literally going to increment it. Now, if the bit on the right-hand side is turned on, I'll toggle the LED. That sound good? If it's turned off, I'll jump over the toggle. That seem like a reasonable thing to do? Now, do we have any instructions which will do something like that? Well, let's look at our instruction list and poke around there a little bit.
Where we can do a compare.
What's that? Oops, don't want that. I think I spent half my life here looking for the instructions. Well, maybe some sort of a jump. How about one of these things? Like skip if bit in register is set, or skip if bit in register is clear. And you give the bit number. SBRC. Let's try that. Where's my code? Now, what's that going to skip? Well, if the bit is clear, we're going to jump over the line that sets the bit. It'll skip that line. Get rid of this comment. Does that seem like that might work? So we need to go back up here. We need these to be zeros again, because we wanted to make it longer than the original timing. Let's compile and see if I broke anything. And let's run. Okay, now I don't remember the original time, but that doesn't look like it's going any slower. Skip a bit and register. We said register 0. I'm pretty sure that's the way it works. Well, let's see SBRC, or we'll look it up. So we look in the instruction manual. Okay. Test a single bit in the register and skips the next instruction if the bit is clear. Well, that sounds like exactly what we want to be doing. Can use any register, uses, yeah, I was wondering if it was 0 through. 0's on the right hand end. And all that stuff just basically says the same thing that we expected it to say. We go here. Okay, where did we do the 20 business? Yeah, we clear it once, make it a 0. We increment it. We should make it have a 1. It won't be clear.
Do we still need to load the high 8 and the low 8 into register 16?
We do. Right here, we need zeros.
Okay.
Very good. Okay, let's see how that works. Okay, that's definitely slower now. Okay, so sorry for the missing that. I'm glad you found it for me. This code just simply says increment this. You make this either set or clear. I didn't pay attention to whether I set or clear it. We'll get exactly the same result if we make it set after the first clock cycle. So I'm just going to leave it as a C and hope one of you fix it if that's the incorrect one. Now, this becomes interesting because does that mean that if instead of bit 20, I check bit 1, I'm actually going to be 4 times as slow? Might be. How about if I check bit 2? Now, I should have highlighted something to you there. Why? Great test question, right? Why is it blinking on and off like that? It almost looks like it's sending me Morse code. Is it trying to get out of the box? Let me put it back at 0 again and look at it carefully. But then if I put it at 1, and you should be trying these as well. Let's go up to like 4. Have you figured out what's going on yet? Okay, well, I'll leave that as a brain exercise for you to try to wrap your head around. And let me see what else I had laying here in front of me. All right, I can't even read that piece of paper. Oh, yeah, I can. That's fine, that's fine, good.
Because it's the multiples of that bit won't light up the LED. Like if it's bit 2, then 8, then if it increments to 8, it won't light it up, even though that's a multiple of 4. We can't hear you, or I can't hear you, Professor.
Okay, I think a cat stepped on something I turned off.
I thought maybe you had gotten it up.
Yeah. The one thing to think about here is that, yes, this very well may have to do with the bits, but write out what's in the counter when you're using the 4. Maybe you should really mask some bits off. Maybe you shouldn't. Maybe you should do it. But more importantly, and probably a more interesting problem right now, is every time we enter the routine and hit this line, we're doing one thing. We're either turning it on or we're turning it off. We're not doing it both in the same interrupt. And so you may want to consider what could be going on there. It could be that it simply has to do with the counter. And remember, we're looking at a specific bit position. And that bit position, if you think about just counting in binary, toggles on at a regular interval and off at a regular interval. But it's on multiple times in a row, or it's off multiple times in a row when you're counting. So you may have to, if you want to slow it more than that, you may have to think of a better solution. Maybe a toggle is not the right thing to be using if you want to go more than 2. So I'm going to leave this as a brain exercise because other than this, I don't want to give you the programming a thing that follows this because we didn't cover some groundwork for it. So your homework assignment is to get this so you feel like you understand how you could adjust the time. And then also see if you can figure out, knowing that the main clock is 16 megahertz. And I think I did some math earlier wrong because I had one number wrong when I computed something. But see, when you were using the 16 megahertz, if you can figure out how long the clock cycles are going to be, can you predict that it's going to be on for a second and off for a second? You should be able to. And, get that kind of in your head. How does the timer really work? What if I only wanted to use the timer once? I wanted to turn it on, wait a while, do something, and then shut it off. I'm not going to use it regularly, but I'll always turn it on, wait, you have it do something, and then you'd have to communicate through a variable, just like we're doing with the CH variable when we're using the USART. What would be different here if we were using both the USART and the timer? Will they get in each other's way? Are they prioritized? Which one is the timer going to happen before the USART, or is the USART going to happen before the timer? What if you're in the middle of processing the USART? That's one of these reasons. If it is going to interrupt the timer, we got to make sure that we've got only the work we need done inside the routine, and we want to make sure everything else gets done outside the routine. So I'll give you some brain thinking. Scan chapter 16 if you haven't, in particular, the registers and the bits and things like that, to get a good feeling for when you're looking at this code, what these data bits are doing. I think we've run out of time. There is one thing I'd like to show you before we go, though, because, and I have written it down so that I didn't forget it, and then I forgot it. But we got time to do it. I showed you earlier that when you're going to be setting bits on, let's say you were using port B. Now, this is not real code here. This is fake code. I wanted to set port B equal to something, and I wanted some bits to be guaranteed to be on. I could do an OR equals. Where is my OR here? If I'm just speaking English here for a moment, where I say 1 shifted over to, I don't say, let's say pin B0 ORed with 1 shifted over to, again, this is not real code, and B2, and maybe ORed with a third thing that you want to have guaranteed shifted over. And you could do something like that to guarantee that when you're done, these bits will all be turned on. And if you leave this on, any previous bits are on. So you need to consider whether you care whether this is adding to or leaving. This does not affect in any way any of the 0 bits. Now it will if you load it into a register, then store the register. But if you're just taking this and you're just setting some bits on or off, this is the notation for combining bits into things where these are values of position. They're not a mask. The opposite of that is, what if I wanted to guarantee that certain bits were turned off? Well, similar to that, except for I'm going to use an AND. If I can ever find the AND. Oh, I'm sorry, I'm putting it in the wrong place. Well, I can't, I have no choice now. I would take these and I would form the word I want, but I'd put parentheses around it. And then I would simply take and I would invert the sense of this with a tilde. So this says, create a bit string and take the 1's complement of it. That means all the 0s now are lined up with places where the AND is going to force those spots to become 0s. And the 0s are where these 1's used to be. So you want to think about those two formulations. One is guaranteed to turn off bits. What bits are we going to turn off? Well, we're going to turn off B0, B2, and B3. The other one is guaranteed to turn on bits. Which ones? B0, B2, and B3, regardless of the values in the other registers. And normally what we would do if we're coding is we would be doing something like load immediate into register 16 of that stuff. And then we'd be doing, you know, a store at some register, at some, you know, timer control register 1. I don't know. I can't even remember the name of the one I'm interested in right now. 1SB. I don't think that's really one, but it might be from register 16. So when we're done in this picture, we're guaranteed that the only the only bits that were guaranteed to be 0 are the ones located at those positions. Every other bit we put in will be a 1. So you use this formulation with an AND to AND it in, and you use the OR formulation to guarantee that 1's are turned on. So think about that, and we'll talk about it in the next episode, which is Wednesday, I guess, for you guys. And we'll also be getting a programming assignment to start working on. So if you're behind at all with this, make sure you get caught up by Wednesday. Remember, I gave you the date of the final exam. It's going to be not this Wednesday, but next Wednesday. The date was the 16th.
Yes.
And a review session on the 14th, which is also when your program projects will be done. Anybody have any questions or comments? If not, I'm done with you for tonight. Okay, I'll see you guys.
Okay.
Good night.
Good night,
Good night.
Professor.
Thank you, Professor.
Have a good
Good
night.
night.
Professor.